I will be talking about one-point functions in large and vector models at finite chemical potential. So, and this is based on two works with Justin David. So I will start with the point that I think many of us know that CFTs at zero temperature are scale independent. Okay, but if you put the CFT at finite temperature, a single length scale arises, which is the inverse temperature beta. So now we consider CFTs on S1 times RD minus 1. Okay, so S1 is the thermal circle of circumference equal to inverse temperature beta, and so because of this thermal circle, the time translation invariance of the theory is broken, and thus the thermal one-point function of the CFT operators are non-vanishing at finite temperature. So while this at zero temperature, these one-point functions are vanishing because of the time translation invariance. Okay, so okay, then the general structure of thermal one-point functions for CFTs at finite temperature, if I consider an operator O of dimension delta O, so then I can write down the general structure as T to the power this delta O times this BO. Okay, so T to the power delta O takes care of the dimensionality of this operator. So then rest of this object has to be some dimensionless object. Okay, so thus this BO can be a function of this mu by T, this dimensionless ratio of this chemical potential mu divided by the temperature T. Okay, and so thus this structure is general. This is a generic structure for any finite temperature CFT, and this BO contains the theory specific information. Right. So then why should we study thermal one-point functions? So there I will mention couple of general motivations. So first, the thermal one-point functions are additional elements necessary to describe a finite temperature CFT completely compared to the zero temperature CFT where it was zero. I mean these one-point functions are zero at zero temperature, but you need this at finite temperature. Now the second one is that thermal one-point functions of conserved currents are useful ingredients in formulating thermodynamics of hydrodynamics of a system. Okay, so then moving forward to a more specific motivation. So these recent studies using calculation in the bulk shows that holographic CFT thermal one-point functions can probe the interior geometry of ADS black hole in the bulk. So considering ADS Schwarzschild black hole, it has been shown that for a primary operator O of dimension delta at boundary, and if you take the large dimensional limit of this operator, the primary operator at the boundary of ADS Schwarzschild black hole, you can see that it has such this exponential structure, and where this tau is the time to singularity from the horizon, and L hot is the regularized distance from infinity to horizon. So tau is what? I mean, if you put a particle on the horizon with zero velocity, a free particle on the horizon of this ADS Schwarzschild black hole with zero velocity, it will eventually fall on the singularity, right? So now the time, how much time it takes to fall on the singularity starting from the horizon, that is I am calling the time to singularity, and that is a property of the interior geometry of the black hole. I think that people can understand that because it's completely, it is calculated based on the geometric properties inside or the interior of the black hole. Okay, so but your calculation, this primary operator are some object which are at the boundary of this ADS black hole, but it can see this property, this time to singularity, which is a property of interior geometry of the black hole. Okay, so then these observations are also generalized for the case of charged ADS black hole with inner horizon structure, and it has been proved using a suitable large D limit. So you can find it in this reference. So I should mention that these observations are universal nature of thermal one-point functions of primary operators obtained from bulk calculations. Okay, so then we pose the question: are there any other simple or universal behavior of thermal one-point functions which can be studied directly from CFT side calculation? So the earlier result which I talked about, that was from the bulk side calculation. So can we study these thermal one-point functions directly from the CFT calculation and look for some simple or universal behavior of this? So then to answer that, we examine thermal one-point functions to examine thermal one-point functions from the field theoretic side or the CFT side, we study large N vector models for bosons and fermions at the conformal fixed point based on the simplifications at large N. Okay, and as some of these theories, means some of these large N vector models, are observed to be a dual to Vassiliev gravity theories, our study should also hold prediction for dual gravity theory in these cases, right? So, okay, then I'll go straight into this. I will summarize my work and the result. So first this model we are studying. So this is a model of N complex scalar fields, and you have a quadric interaction term in the action, and so this capital D mu are covariant derivative because of the presence of chemical potential. So it appears in this way, and so the theory is, of course, S1 times RD-1 because we are studying the finite temperature CFTs, and also to mention that we are studying these models in odd dimensions or space-time dimension, where D is equal to 2k plus 1 and k is integer. Okay, so now at large n you can find a non-trivial fixed point by taking lambda going to infinity and k being odd. So you can notice that for k to be odd, for k being odd, you will have this D equal to 3, 7 and so on. So it's alternative odd dimensions starting from D equal to 3. Okay, so and also for clarification, I should mention that you have, by putting lambda equal to 0 and mu equal to 0 in this model, you will recover the free CFT, free bosonic CFT at finite temperature. Okay, so these are the two points. One is non-trivial fixed point I specified, and also the free CFT point obtained by this. Okay, then I will mention another, or clarify this non-trivial fixed point a little bit more. So this non-trivial fixed point is described by a thermal mass MTH, which satisfies the gap equation or the large N saddle point equation of the action obtained after use of Haber-Sturm-Weierstrass in the path integral. Okay, so although I won't give much detail about it. Okay, so let's then the obvious questions will be what are the operators or whose thermal one-point functions we are going to study. So these are the schematic form of those operators or the higher spin currents. So you put these fields here and you sandwich L number of covariant derivatives inside. So you can recall that these are the capital D's, and you have N number of second derivative or the second covariant derivative inside. So this is a schematic structure of the operator whose thermal one-point function we are going to study, and the thermal one-point function of such operators are denoted by this notation AO. So N and L, you can see that L is this number of derivatives or the covariant derivatives, and N is the number of second covariant derivative. So to give some context, I should mention that for L equal to 2 and N equal to 0, this operator represents the stress tensor of the theory. Okay, so then the next part is that how do you evaluate these thermal one-point functions of such operators? Okay, so to evaluate that, we use the fact that the thermal one-point functions appear in the operator product expansion of thermal two-point function. So given the thermal two-point function, thermal one-point functions of arbitrary spin L are evaluated by applying OP inversion formula at finite temperature. So this was developed by these authors, and also this OP inversion formula is generalized for the case of case with finite chemical potential by studying the two-point function of two-state fields. So this has been parallelly developed by us and also these authors. So okay, then I should mention that thermal two-point functions are known both at non-trivial fixed point as well as for the free CFT point, which I specified about these two CFT points, the free theory and the non-trivial CFT. Yes. Right. Twisted field means, can I write down or at the end? It's just like you redefine your field by phi to be a defined phi tilde times e to the power I mu. So you just make the time so that it just falls. Derivative, the covariant derivative just acts as the normal derivative. So that's the way. Maybe towards the end I will just write down the thing. Yeah. So okay. So then thus we can, as we know the thermal two-point function for both the points, we can directly apply these methods to obtain the thermal one-point functions of these operators. Although I am not giving all the details of this method, but I will mostly focus on the result which we obtain by using this OP inversion formula. So I directly give you the result by applying the OP inversion formula on the 2-point function. We get the 1-point function which has this expression, and this MTH is the thermal mass which satisfies the gap equation, and with this choice of beta to be 1. Okay, so then you can you have a cross check for spin 1 and spin 2. Spin means this L equal to 1 and L equal to 2. So you can cross check this result against the, you can calculate spin 1 and spin 2 current directly from the partition function, and you can see that it agrees with the above answer, which is obtained from the OP inversion formula, obtain oval constant factor. That is because in this OP inversion formula method you also have the the structure constant and the the OP coefficient inside this. So that's why this oval constant factor appears, but you have a cross check for this spin 1 and spin 2 current. Alright, so then as I promised that finally our goal will be to obtain the thermal 1-point function of these operators, and then we will look for whether there are some simple or universal nature of these thermal 1-point functions which we can find. So the first one which we have found is that large L or large spin limit of these operators. So at large spin limit, what is observed is that thermal 1-point functions evaluated at the non-trivial fixed point of the theory tends to the free theory 1-point function at large L up to a mu dependent factor, which is either cos hyperbolic mu or sin hyperbolic mu for even or odd L respectively. So mathematically it looks like this. So you have the thermal 1-point function at the critical point or the non-trivial fixed point, and you take the large L limit of this thermal 1-point function at the critical point, and that is equal to the large L asymptotic value of the free theory 1-point function times this cos hyperbolic mu and sin hyperbolic mu for L even and odd respectively. So you can see this nice factorization of this chemical potential dependence here. And okay, so then I just mentioned that this A free is the large L asymptotic thermal 1-point function for the free theory. Okay, so then the next observation is that for large space-time dimension, you can see that the thermal 1-point function evaluated at the non-trivial fixed point becomes exponentially suppressed in D compared to the free theory. So you evaluate the ratio of the critical, the thermal 1-point function at the critical point or the non-trivial fixed point divided by the free theory 1-point function, and you take the large K limit. Large K is equivalent to large D limit, large space-time dimension, and you can see that it is exponentially suppressed in K, and you have some these factors of chemical potential dependence. And I should say that this L and mu, the spin and the chemical potential are kept fixed while this K is taken to infinity. And also for the earlier case, when you take this large L in this case, you kept this space-time dimension as well as the mu, the chemical potential, fixed at large L. Okay, so then we have observed similar, we have similar observations for Grotz-Neumeier model for fermions at large N. And so again you have this n number of Dirac fermions, and you have a 4 Fermi interaction term, quartic interaction term, and then you study at it in odd space-time dimensions. And so you can again find a non-trivial fixed point with large lambda going to infinity, but for K being even. So I think you have noticed that for the bosons it was K being odd, so it was 3, 7 and so on, but here you have D equal to 5, 9. So in the alternative odd dimension, the bosonic model and fermionic model exists. Okay, so then again this lambda equal to 0 and mu equal to 0 refers to the free fermionic CFT. And so here this for this fermionic model you have to you have various classes of operators in your theory. So the first one, this one is very similar to the bosonic operator. So you have just L number of derivatives or covariant derivatives and n number of this second covariant derivative. But for O plus you have an extra gamma mu 1 here, and then rest of the thing is the same. And for the O minus you have a gamma mu del mu contracted, and then rest of the thing is very similar. Okay, so then of course the goal will be to evaluate the thermal 1-point function of all these such classes of operators constructed out of fermion bilinears. Okay, so then we have generalized this the method of OP inversion formula for large n vector models of fermions, and this method can evaluate all these 3 different classes of operators from the once you are given the thermal 2-point function of the theory. Okay, So then again we have the similar observation that your critical, the thermal one-point function at the critical point or the non-trivial fixed point at large L becomes equal to the large L asymptotic answer for the free theory times this factorized, the chemical potential factorized in this manner. And then for the large D also you have the same observation that your the ratio of the critical, the thermal one-point function at the critical point divided by the free theory thermal one-point function has this exponential suppression. Okay, so then and I think just by looking at the formulas which I have shown, that this RF, you have the exactly same formula for the RF for both boson and fermions. Okay, so that's what it's been shown here in this graph. So these blue and red points are respectively bosons and the fermions. So in the alternative odd dimension, so we are plotting this ratio here, and so these points are actually numerical values of the function, and this black solid curve is the asymptotic answer which is shown here. Okay, so and that agrees at a large k. Yeah, so yeah, and this for k equal to, you can also notice that k equal to even and odd in alternative odd dimensions, the fermion and boson appears alternatively. Okay, so and also for mean field theory we have similar structure at large L. So this is the answer for the mean field theory, and you can see that you have that nice factorization of this chemical potential, and the rest of the thing is a L dependent factor. Okay, so now there I will talk about another particular specific dimension. So this Gauss-Nevieu model at d equal to 3, and so if I go ahead by studying the thermal one-point functions of higher spin currents obtained using OP inversion formula for Gauss-Nevieu model in d equal to 3, we have the observation that at a critical value of the chemical potential mu equal to mu c, given by this value 1 by beta cos inverse 3 by 2, the thermal one-point function of higher spin currents including the stress tensor exhibits branch cut singularities in the chemical potential plane. So this looks like this. So the stress tensor at this point behaves as a branch cut singularity. So you have this mu c minus mu to the power 3 by 2. Okay, and the observation is that for stress tensor the critical or the spin to current, so the critical exponent is 3 by 2, while the other currents till L equal to 4 shows critical exponent of half. So that you can see here. So this, the spin to current has this mu c minus mu to the power 3 by 2, while the up to L equal to 4 all other currents has this square root sort of branch cut. Okay, so then based on this, this branch cut structure of 3 by 2 for the stress tensor, you can see that it coincides with the in the literature about the Lee-Yang singularity for repulsive core interactions. So in this article you can find such expansion of the stress energy tensor, and then it is observed that the exponent phi equal to this phi is equal to 3 by 2 is special for mean field theories with repulsive core interactions. Okay, and as our stress tensor has the exactly similar critical exponent, thus we can identify this point mu equal to mu c as a Lee-Yang singularity for Gauss-Nevieu model in d equal to 3. Okay, so and also we have proved that the thermal expectation value of the class of currents O plus are real in this range of for this chemical potential lying in this range, and that resulted in the non-trivial identity of Bernoulli polynomials given as here. So and then the class of operator A O naught attains purely imaginary thermal expectation values in the same domain. Thus the theory is outside the unitary regime. Okay, so then I will conclude and give some future directions. So we have evaluated thermal one-point functions of higher spin currents for large N vector model of complex scalars and fermions by the use of OP inversion formula at finite chemical potential. Then we have observed simplifications of thermal one-point functions of higher spin currents in large N vector models at both large spin and large d. And finally we have identified the Lee-Yang singularity point of the Gauss-Nevieu model for d equal to 3. Okay, so then a couple of future directions. So it will be interesting to generalize the OP inversion formula for CFTs on other geometries like S1 times SD minus 1 or S1 times some HD minus 1, and examine if thermal one-point functions exhibit similar simplifications at large N and also large D for CFTs on other geometries. And one more ambitious exploration would be to investigate if the simplifications are properties of thermal one-point functions for any general CFT at finite temperature. Okay. So yes, thanks.
Hi, thanks for the nice talk. I wanted to ask you that this non-trivial fixed point that you're using in the CFT, is it an IR or a UV fixed point?
Depends on the dimension. So in d equal to 3, you have let's say d equal to 3 scalars, then it's a IR fixed point.
Okay.
But across the dimension it flips.
Okay.
So if you just go ahead in the d equal to 7 and all, then
yes.
it becomes and also for fermions you have let's focus on d equal to 3. So for bosons it's a IR fixed point, but for fermions in d equal to 5 and all it is UV. Yeah.
Okay, so is there a function that sees this transition happening?
Yeah, you can see it. Yeah.
Okay, thanks.
Other questions?
You can see this something called F theorem and C. You can see that.
Hi. So in this bosonic and the fermionic vector models, so you can estimate the central charges, right, from the one-point functions.
Not necessarily. These are higher dimensional CFTs.
Okay. So there is no you can't calculate, or is there any notion of central charges in those CFTs?
From thermal one-point functions, you cannot talk about that.
But from the stress tensor?
No, it's not. I think you are just saying that for 2D, that from the stress tensor you can talk about.
Yeah.
But for higher dimension, you cannot.
Okay.
For d equal to 3, why it is non-unitary? D equal to 3 Gross-Navier.
Gross-Navier model is non-unitary because you can find that there is a gap equation, right? How these CFTs are defined. So at finite temperature, you define. So I had mentioned that you use a set of. It was written in words, but so let's say here. Yeah, so we use these methods that we first do this Haber stoichiometry, and then there is you get some expression. So then you have to analytically continue or somehow put a cutoff to define it. So then if you do that, you will have a gap equation. So gap equation is that what should be the thermal mass of your theory. Okay, so then for d equal to 3, the gap equation looks very simple. Maybe I can write down the gap equation. So it is some mth plus 2 log 1 plus e to the power minus mth. So beta is equal to 1, that I have assumed. I am choosing it like that. So then if you solve it, you can see that thermal mass, this mth will be, it's never real. It's never real. So in that, with the chemical potential, there will be a chemical potential term. So this is 2 real of mth plus I mu or something. So there will be one plus mu term and another minus mu term. Okay. Plus mu plus log 1 plus e to the power minus mth minus mu. Now if you solve it, you will see that this thermal mass is never real. So then that means that it's just looks like the mass in the theory.
Okay.
So it's not unitary. And also you can see that I didn't show these details. So in the thermal one-point functions, one class of thermal one-point functions are imaginary, purely imaginary. So that also says that it is. For the bosons, it's real. It's thermal mass you can find, it's real, and all the thermal one-point functions are real. So that is a good theory. It's not. There is no specific reason, but for calculation simplifications, I guess. Because n equal to 0, finally it is it's just like you are putting a derivative. So if you have a mass, so then there will be some set of terms, so that will be proportional to that MTH, right? Similar terms with an extra factor of MTH, or I mean whatever the number of del square is there. So yeah, and what you are asking, so we redefine the field in this way, that okay.
Other questions? Okay, no more questions. Let's thank Srijan.